All right. Okay, so we have increasing and decreasing functions. So the theorem, this is the one we'll be using the most. This theorem right here. I hope I can erase this circle. Okay. Oh, you guys can't see the circle. Interesting. All right. So we're looking at this theorem right here. Test for increasing and decreasing. So this is when you use the derivative, okay? And if it's positive for all values in that open interval, then it's increasing on that closed interval. Okay? Be careful, that function does have to be continuous on that closed interval. Now, this theorem is kind of hard to read. It'll make more sense when we start using it. Right? So if the first derivative is negative, then the function is decreasing. If the first derivative is 0 for all x, notice this is all x, not just some one point, then f is a constant. That means it's not increasing or decreasing. All right, so that's like a constant function. All right. Guidelines. You guys can read guidelines on your own, yeah? I gotta erase this or it's gonna get on my nerves. How do I erase it? You guys can't see it. Here, can you? Oh, I erased it. Okay. What am I going? How do I get back? All right. I don't know what I'm doing. All right. First derivative test. So this theorem is about increasing or decreasing. And then this theorem is the first derivative test. Okay? So this is one of those pain in the butt derivatives. It has a name, but they won't let you use a name. They want you to say it in words. Okay? If the first derivative changes from negative to positive at a point, then f of c is a relative minimum. So you actually have to say that when you justify your answers. You say that the derivative changes from negative to positive. That's why you know it's a min. A derivative changes from positive to negative. That's why you know it's a max. You're not allowed to say by the first derivative test. Okay? You have to actually state that first part and the second part. I'm sorry, the first part. Right? The if part. The third one, if the derivative does not change the sign at c, then it's neither a max or a min. Okay.
Real quick, can you explain the difference between a closed and an open interval?
Okay, what's the difference between a closed and open interval? I'll just do it on the back of this paper. So if I have, say, 2, 3, that means it's an interval that includes the endpoints. So an open interval, that means don't include the endpoints. So if I were to look at this on a graph, so if I wanted to illustrate this version, I'd have something that looks like this. If I wanted the open interval, it would be open circle and open circle. So don't include the endpoints. Okay? Does that answer your question? So, again, the important part is when a function is increasing or decreasing and the first derivative test. And you have to state these parts. And I will do some examples of that, hopefully. And I lost the second page.
Do they go hand in hand, or are these just two?
Yeah, they're related. In fact, most students actually confuse the two of them. They think this is the first derivative test, and they forget this one exists. All right? So this one is only saying whether it's increasing or decreasing. This is telling you whether it's a max or a min. Okay? So if I ask you whether it's increasing or decreasing, I am not asking you to find a max or a min. I'm asking you for the intervals of increasing or decreasing. Okay? So that's this term, where you just when you answer the question of whether a function is increasing or decreasing, if I'm asking for a max or min, that's the first derivative test. Does that answer your question?
Mm-hmm.
Okay. All right. So here are some examples. And let me get this out of the way. All right. Okay. A function is strictly monotonic. This kind of came out of the blue. Strictly monotonic if it's going to be increasing or decreasing for the whole interval. Right? So that kind of makes sense. If it's like going up the whole time, it doesn't have to go up like straight, but as long as it's always going up, that's considered monotonic. Or if it's always going down, that's considered monotonic. This is not monotonic. Right? This is not monotonic. But usually monotonic functions are boring. You know, like monotone people are bored. Well, maybe that's not true. All right.
Bueller.
Huh?
Ferris Bueller.
Oh, the teacher, right? The history teacher. All right. Okay. So the following functions determine intervals of increasing, intervals of decreasing, and all relative extremes. That's also another confusing part. They usually ask all that stuff in one question, so you think they're all using one theorem. Well, intervals of increasing, intervals of decreasing is using one theorem, and then the relative extrema is the other theorem. Okay? So it's two separate theorems, but they are related. They're just interlocked together. All right, so let's take the derivative first. So that's 3x squared minus, what's that, 3x? Yes, no?
Yes.
Okay. Critical numbers, so that means you set it equal to 0 and solve. So that'll be 3x times x minus 1. So x equals 0 and x equals 1. Sine chart, well labeled. What does that mean? All right, so we'll draw a line. I want 0, 1, and this is the first derivative. Okay, now sine chart. So there are two ways to make this sine chart. The way I prefer is least amount of work. But if that confuses you, you can do it other ways. Okay, there's at least 3 ways to do this.
Is
Okay.
this like the particle motion thing?
No,
No.
not that you can't get to the particle motion thing, but this is not. So you have to do this all the time, but it won't be particle motion all the time. Okay? All right, so the way I like to do this, you go back to the original derivative, okay? Do you know what shape that is? What shape is that if you graphed it?
Parabola.
It's a parabola, right? And which way is it facing?
Up.
Up. So if you know it's facing up, and you know it crosses the x-axis twice, does it look like this? Does it look like this? Does it look like this or this? So if this is A, and that's B, and this is C, this is D, which way does that graph look like?
A.
It looks like A. So remember, if it's above the x-axis, it's positive, so these are positive. And if it's below the x-axis, it's negative. So that's a quick way to just make a sine chart here. Positive, negative, positive. So, and they actually don't get that creative. Parabolas come up a lot. Okay, parabolas come up a lot as a derivative. Okay, so you can quickly make a sine chart. Now, if that confuses you or you think you're going to have a hard time remembering that, another way to do it is just plug in numbers. So I can plug in any number in this region, say -1. You could just plug it into the original or you plug it into the factored version. Either one is fine. I'm going to do both, okay? Because I prefer, if I were to do it that way, like let's say it's not a parabola and it's like a 5th degree polynomial, then it's easier to just plug it into the factored version. So if I plug in -1, I get -3 here, and I get -2 here. -3 times -2 is +6, so it's positive. Yes? Okay? And then plug in 1/2 in here. So if I plug in 1/2, that would be 3/2, and 1/2 minus 1 is -1/2. And I'm going, well, I don't really want to multiply those fractions. But if I multiply them, what sign do I get? S-I-G-N.
Negative.
Negative, so it's negative. So even if I don't really know what the product is, you really just want the sign anyways. Right, positive or negative of it, so it's negative. Then pick another number, say 2. So if I put 2 in there, I get 6 times 1. Agree? 6 times 1 is positive, so it's positive. So that's another way to confirm this sine chart. Of course, you could have done it with the original, okay? You just make sure when you plug it in into the factored form, it's not that different from the original. Like sometimes you divide by 3, right? If you didn't divide by it, then you're safe. Because sometimes there's a negative number up here, and if you divide by that negative number, when you're solving it, you've screwed up your signs. You understand that? If that were a negative number, and you got rid of it in your process of solving the problem, you have screwed up your signs. So just be careful. So if you're doubtful of your attentiveness to what you have, just go back to the derivative. Okay? All right. So now, where is it increasing? So look at here. It's increasing where the first derivative is positive. So it's increasing from negative infinity to 0 and from 0 to infinity.
Let's put union.
You know what I noticed? I put union, but AP doesn't seem to care. You can just put commas. And where is it decreasing? It's decreasing between 0 and 1, where the sign is negative. Yes?
Wouldn't it be 1 to infinity?
Yes?
Do we,
Huh?
so it's all in parentheses because of the union?
You have to speak louder.
It's all in like parentheses, no brackets because of the union.
Okay? It's no brackets because whenever we talk about intervals of increasing and decreasing, you will not include the endpoints. Whenever you talk about intervals of increasing or decreasing, you will not include the endpoints. Okay? All right. And then relative minima. So remember, so this is saying it's going up and then going down. So I always like to picture it as it's going up and going down. So that's a max. So there's a max at x equals 0. This is now going down and going up. So there's a minima at x equals 1.
So that's a max of
The original function. So when I say there's a min or max, I'm talking about the original function. I'm not talking about the max or minimum of the derivative. Okay? And if I want the actual y value, I have to go back and plug it into the original. So let's do that. So it'll be 1 comma, plug in the 1, I get negative 1/2. And if I plug in 0, I get 0. Questions? Okay, move it. Yes, go ahead.
Will we, like have to plug it in, like plug in the numbers for the relative maxima or minimum? Or
Generally speaking, they want the coordinates.
will the critical numbers be?
Huh?
Like, will we have to look for other numbers besides the critical number if they're not the max and minimum?
Yes. If it's a closed interval, they might ask you for the absolute extrema, and you have to do the endpoints. But notice this one, this was an open interval, right? This is all real numbers. So I didn't have to deal with the endpoint.
Is there an example in here?
Here.
Oh, sorry.
So this one, though, it's an open interval, so you're not going to check the endpoints on this one either because they didn't include it.
Okay.
But this is a open interval, but it's a finite interval, while number 1 was an infinite interval. Right? This is all real numbers. Number 2 is an open interval, but it's only between 0 and 2 pi. So let's take the derivative. What are the critical numbers? So you set that equal to 0. And that gives you cosine x equals 1/2. So x equals... Maggie!
No.
You made eye contact. So, what is cosine equal to 1/2? On this interval, from 0 to 2 pi. So the unit circle.
Pi over 3.
Uh-huh.
Oh my gosh.
Where's the other one?
Oh.
You got it.
Then it's in this one. No. It's in this quadrant.
Okay, 5 pi over 3.
Okay.
Alright.
So that was my third guess.
Alright, so you had the pi over 3. You know it's in the fourth quadrant, right?
Yeah.
Just subtract that from 2 pi. 2 pi is 6 pi over 3, so 6 minus 1 would be 5. Okay. Alright. So, well-labeled chart. So this time you have a 0 and 2 pi in here. And you have a pi thirds and a 5 pi thirds. Okay. So this time, I'm actually just going to plug it into the derivative. There's no like factoring or looking at the graph for me. So what's a number between 0 and pi thirds? Huh?
Any number? Or?
Pi 6. Yeah, don't just tell me like 0.7. That doesn't help me at all. Actually, I'm not even sure what 0.7 is. But I know pi 6 is in there.
Yeah.
So what's cosine of... Uh-oh. What's cosine of pi 6? Sorry.
Root 2 over 2.
Root 3 over 2. So it's 1 minus root 3 over 2. Is that positive or negative? So that means, do you know whether square root of 3 is bigger or smaller than 1?
It is. So it's negative.
What do you mean it is? I said, is it bigger or smaller?
It's bigger than 1.
It's bigger. All right, so that's negative. Here's a hint. If you're pressed for time and this is a trig function, it's just going to alternate. Negative, positive, negative. But let's double check. So what's the number between pi over 3 and 5 pi over 3?
Pi over 2.
Pi over 2. Or even just pi.
Yeah.
Right? Pi is probably easier. What's cosine of pi, Stacy?
Cosine of pi is negative 1.
Negative 1. So it's 1/2 plus 1. So that's positive. Okay. What's between 5 pi over 3 and 2 pi? This is a little harder.
11 pi over 6.
11 pi over 6. Okay, so Mason, so what's cosine of 11 pi over 6?
That would be root 3 over 2.
Root 3 over 2. So remember, 1/2 minus root 3 over 2 was negative, so it's still negative.
Right.
Alright, so there's our sine chart. So we say it's increasing from pi over 3 to 5 pi over 3, right? Because that's where it's positive. And well, F prime, well labeled F prime. All right. Decreasing from 0 to pi thirds and 5 pi over 3 to 2 pi.
Oh.
And then the relative minima, remember, so if I saw this sine chart, it's just easier to just make these little symbols. You know what I mean? It's decreasing, then increasing, increasing, and decreasing. You know what I mean? You know what I'm talking about?
No,
So then I have a minimum at pi thirds. So there's a minimum at pi thirds. At x equals pi thirds, there's a minimum, and there's a max at 5 pi over 3.
For right now, do we need to know like the y value too, or is it okay if we just do x equals, let's just do the x value?
It's really just directions. Like, what do the instructions say? Like half the time they'll say, at which x values is there a minimum? And then sometimes they'll say, what's the actual maximum? So if they're actually asking for the maximum, which is kind of implied here, you have to find the y value. Okay, so let's go ahead and find the y value here. But remember, to find the y value, you have to go back to the original function.
That's not going to be fun.
Yeah, so it's 1/2 pi thirds minus the sine of pi thirds. What's that? Pi 6 minus, what's sine of pi thirds? Danny.
The sine of pi thirds
Yeah.
would be 1/2. Right? No. It's square root of 3.
Square root of 3 over 2. So this would be pi thirds, pi 6 minus square root of 3 over 2. This one's 5 pi thirds. Plug that in, so it's 1/2 5 pi thirds minus the sine of 5 pi thirds. So what's that? 5 pi over 6 minus, what's the sine of 5 pi over 3? That's negative, isn't it? Root 3 over 2. So 5 pi over 6. Oops, not a comma, plus sign. Root 3 over 2. Wow, that's a math.
That's statistic.
Yeah,
How we doing on?
We've got like 20 minutes.
Awesome.
Wait, why did we do?
Ask. Why did we do what?
Why did we plug it back in?
Because it's asking for minimum and maximum. And minimum and maximum usually implies the y value.
Okay.
Alright?
And, oh, okay, I see. Sorry.
No problem. Okay, here we go. Number 3. Derivative.
Oh, Lord.
2/3 x squared minus 4 to the negative 1/3. Continuing with the chain rule, multiply by 2x. Clean that up. 4x in the numerator, and then 3 and cube root of x squared minus 4 in the denominator. Agreed?
You were very fast.
Agreed.
Yeah?
Yeah.
Okay. Critical numbers. Set the numerator equal to 0, and I get 0. Set the denominator equal to 0. 3 times the cube root of x squared minus 4 equals 0. Divide by 3, so you just have cube root of x squared minus 4 equals 0.
Wait,
Q-
so for critical numbers, you have to do the top and the bottom?
Okay, so good question. So the critical numbers occur when the derivative is equal to 0 or when the derivative is undefined. Okay, so setting the numerator equal to 0 is when the derivative is equal to 0. Setting the denominator equal to 0 is when the derivative is undefined. Does that answer your question? All right. So now I cube both sides and I get x squared minus 4 equals 0. So I get x equals plus or minus 2. Now, one danger of the whole set the denominator equal to 0, now you have to check to see if these numbers are actually in the domain of the original function. Right? What is the domain of the original function? Well, it's a cube root. There are no problems whatsoever. Right? It's even roots that have problems. Odd roots have no problems. So this function, the domain is all real numbers. So yes, plus or minus 2 is in that domain. Okay? All right. A well-labeled sine chart. So this is f prime. And we want -2, 0, and 2.
Why did they specify well labeled?
I don't know. Maybe because people don't label it, but I don't know what that means. Maybe mine aren't well labeled. All right, so let's plug in a number here. -3. So this is really messy. So I would go back to my original derivative where I didn't really simplify it much. So plug in -3, what happens? So the numerator is negative, right? I got -12 in the numerator. And if I plug it in there, that'll be 9 minus 4, right?
So it's negative.
Right, so it's positive down here, whatever it is. I don't know what the number is. It's cube root of 5 or something, right? So that's going to be negative,
But it doesn't matter.
right? Because I only want the sign. You're right. I only want the sign, S-I-G-N. Plug in -1. Plug in -1, I have -4. And 1 minus 4 is -3, so it's negative down there. So negative divided by negative is positive. All right, so I plugged in -1 and got positive. Plug in +1, that'll be +1, and then negative in the denominator. So it's negative. Plug in 3, positive, positive, positive. So if you are hard pressed for time and you don't want to sit there plugging all those numbers, plug in the first one and then just alternate. 95% of the time that works. So if you're pressed for time, just wing it.
We're going to do that for this test, and we're all going to be...
No. I will guarantee it won't work for one of them. I will guarantee it won't work for one of them.
Of course.
Well, 5 times not bad.
Okay? But I want to show you how to spot those where it won't work for it. Well, I'll tell you now. So if there's an even power, it won't work. Right? Because the signs don't change on an even power.
Oh.
Right? So whatever critical number that even power gives you, it won't change around that. So if this were 4x squared equals 0, 4x squared, that means around the 0, it won't change signs. Did you understand that? So if this were 4x squared that means the critical number it gives you is x equals 0. So that means the sign won't change around x equals 0. That's it. That's the time it fails, when it's an even power. Okay? All right. So let's look at the increasing. So increasing is between -2 and 0, and 2 to infinity. So -2 and 0, and 2 to infinity. Decreasing from -infinity to -2, and 0 to 2. So there's a so here, easy. So that way, that way, that way. So there's a minimum at x equals -2 and 2, and a maximum at 0. Let's get the y values. So it's at -2 comma 0, and 2 comma 0, and at 0 it's what is that? Cube root of 16?
How do you do that?
Cube root of 16.
So you plug those.
Oh,
back
so I just plugged in -2 into this thing. Oops.
the original, right?
Yeah, the original. That's how I did it so fast, because it's just there.
Yeah.
Oh, number 4 is very unfriendly. All right, ready? Questions? Pausing.
So
Yes.
problem with number 4, when you take the derivative, do you have to use the quotient rule, or can you take the exponent and do like negative exponent, or is that annoying?
Okay. In fact, I was about to address that. So looking at number 4, do you want to take a derivative as is, or you want to mess with it first? I personally would mess with it first. Like quotient rule for this. Now, there is sometimes they give it that way because if you use the quotient rule, it simplifies nicely. And if you don't do the quotient rule, it won't simplify well. So you decide, do you want to take the risk? Maybe they give it to you that way for a reason. Because they could have given it to you this way, right? X squared plus x to the -2. All right, this one looks really easy to take a derivative of. And I still want to take a derivative of this one instead of that. Everybody understand how I got this expression for number 4? Right, so I'm dividing each one separately. X to the 4th divided by x to the 2nd is x to the 2nd. And 1 divided by x to the 2nd is x to the -2. So that's it. How we doing here?
Say that again.
Alright, so I'm dividing here, so x to the 4th divided by x squared is x squared.
Okay.
And then 1 divided by x squared is x to the -2. So if I have 1 divided by x squared, right, that's the same thing as x to the -2. Okay. So in fact, I think I want to go this way. We'll see what happens. If it's horrible simplifying, then we'll just take the hit. All right, so the derivative will be 2x minus 2x to the -3. And then you go, yep, we're going to take the hit. Why am I saying we're going to take the hit? Because if you go do the critical numbers, you're setting this equal to 0, right? Which means you have a fraction. And if you have a fraction, you need one fraction. So this is going to be 2x to the 4th minus 2 over x cubed equals 0. You have to have one fraction, not two fractions. You see how I got this fraction? Right, it's just x cubed is a common denominator, so I had to multiply that by x cubed again. Now, so when is this undefined? This is undefined at x equals 0, but 0 is not in the original domain. So you can ignore that critical number. Well, so x equals 0 is not a critical number, even though the derivative is undefined. But here's the bad news. You still have to make it part of your Sine chart. You want points of discontinuity to be part of your Sine chart. Not just critical numbers, you want to include points of discontinuity. Because weird things happen when it's not continuous. So I say again, when you make a sine chart, you're not just including critical numbers, you're also going to include where it's not continuous. Okay? Alright, so if I take a 2 out of that, what do I get? So now I'm finding the critical numbers, so I'm going to go ahead and take out a 2. So it's x to the 4 minus 1. So this is going to be x squared minus 1 times x squared plus 1. So that means this has zeros at x equals plus or minus 1. So my critical numbers are at plus or minus 1, but I have a point of discontinuity at x equals 0. I have critical numbers at x equals plus or minus 1. I have points of discontinuity at x equals 0. So that's how I'm going to label my chart. -1, 0, 1. Now, so the question is, which of these versions of the derivative do I want to use? You pick. None of them look any good.
Probably the last one.
This one?
Yeah.
All right. So let's plug in -2, right? I'm putting a point to the left of -1. -2 in the denominator is negative, right? Negative number to an odd exponent is negative. So you don't have to figure out that -2 to the third is -8. You just have to know the sign. -2 to the fourth is 16, 32, 30, 30 over -8, so it's negative. Is that too fast? All right, plug in 1/2. Oh, yeah. So 1/2 makes that 1/8.
-1/2.
Thank you, -1/8. Plug -1/2 there, it turns into positive 1/16. Now I'm going to have to start writing things down because I'm losing track. So if I plug in -1/2, I got -1/8 in the denominator. And that's 2 times 1/16 minus 2. So that's 2/16 or 1/8 minus 2. That's negative, yes?
Yeah.
Over negative makes it positive. Now plug in positive 1/2. So the denominator is positive, but the numerator is negative. Yeah? It's the same as this one. So now it's negative. Negative over positive makes negative. Yes? Okay? Now plug in 10. I'm choosing 10 because it's obvious that this is going to be positive in the numerator, and positive number in the denominator is positive anyways. So it's positive. You have a question, Peter? So the intervals of increasing, there's 2 of them. So it's -1 to 0 and 1 to infinity. Intervals of decreasing is -infinity to -1 and 0 to 1. Minima. So we're talking here, here, there's a max. So there is a minima at x equals -1 and 1, and there's a maxima at x equals 0. Oh, is that true?
No, because 0 is undefined.
0 is undefined, so no. There's no max. Alright. Okay. So what do we got here? So we got so there's none. There's no absolute maximum because x equals 0, not in domain. Alright. So we're going to plug in -1 into that expression. That'll be 2. Right? Is that right?
Yeah.
And they're both 2. Questions?
So, we didn't do it for the first one, but we should always plug.
We didn't do it for the first one? What do you
We
mean
should
we
always
didn't do
plug
it?
in the extrema back into the original function.
Oh, that one.
You mean this first one?
Yeah.
We did though. We did.
I must have missed that. Okay.
Alright? How we doing on time?
5 minutes.
5 minutes. Oh. Okay, so this is just example, more example, more example. So you know enough to do your homework, okay? But I can't start the class with this tomorrow. Alright? What I want to do now is give you a chance to make problem requests for me to video from last night's homework.
Friday.
Huh?
Friday.
So what does that mean?
Is it?
There's none tomorrow.
Okay. Alright. Any requests or no?
Number 64.
64?
Yeah.
I think I was good at everything.
I think 17.
17?
Oh yeah.
Maybe 23.
23?
Yeah, 17.
else. 47.
47?
While we were doing our homework, were we supposed to like state like it's continuous and differential?
It depended on the instructions.
Mm,
I mean, the instructions usually answer those questions. What you're supposed to do.
Can I get the sheets? The answer.
Oh, yeah. I already finished. Is that it?
Thank you.
Okay. While you're putting it away, and if you just want to watch what's going on, that's fine. So, note, they're giving you the graph of the derivative, right? In these problems, they're giving you the graph of the derivative. So, the sine chart for this, for the derivative, so you want to find these x values here, which I can't see. What are those x values? So, they're regular numbers. All right, so -2. So, it's crossing there, so at -2. Well, you could put the 0 on there, even though nothing happens there, and then +2. So it's negative to the left of -2. It's positive here and positive there, but it's negative there. Does that make any sense? Right, it's all positive in between these two. So this one, I have x equals 1, and what's that, 5? And 7. Those are my breakpoint, where it crosses the x-axis. So the derivative is positive here, negative in there, positive between 5 and 7, and then negative after that. So that's what they're asking for the sine chart.
Alright.
And then it says f of x is increasing on, and you're going to put the interval in there. So f of x is increasing on -2, -2 to +2. So it's -2 to +2. That goes in that blank.
So we don't even have to worry about the 0 in the middle?
Good question. Do you have to worry about the 0? No.
Okay.
Alright? F of x is decreasing on, so this time you have two intervals, so that would be -∞ to -2, and 2 to infinity. Right.
So do you want us to do this sheet?
Yeah. But I'm non-committal on that. You can do it if you want. I'll go over it on Monday. F of x has a relative max value at, so where's the max?
2.
Right, x equals 2. Oh, what's the maximum value? That part you can't answer. I don't know. You need the actual function to draw that conclusion. Do you understand? To get the actual max, you need the function. And they don't give you the function, so you can't actually find that value. Okay? F of x.
Can we get it like from looking at the graph or?
Now, you might find the absolute max occurs at such and such a point, but you don't know what the actual maximum is. Because remember, when you take the derivative of a function, the constant disappears. So you don't know how much a constant there is. So there's no way to tell what the actual maximum or minimum value is.
So is there not a max at the -2 because it's a point?
It's a min. Remember, this is the derivative, not the actual function.
That's the derivative?
Yeah, this is the derivative.
Oh, I
Final
see.
that. Okay. All right. Have a good weekend.